In this video, we will be looking at finite difference methods or a finite difference approach. So this is a different approach from what we've seen in the previous video, where we've seen how to use analytical solution to find the temperature distribution in a particular body. But in this particular video, we'll look how we can use a numerical method or a numerical technique to find the temperature distribution. So let's dive into it. So often what happens is that your geometry or your object isn't regular or isn't trivial. So it's not always that you'll have a rectangular or a circular or a cylindrical body for which you will have a particular analytical solution. So so in that case you need a different technique to find the temperature distribution. So what we do is we use a numerical technique like a finite difference technique to find the temperature distribution. Now what this numerical technique is that it uses uh, numerical solutions to determine temperature at discrete points. Okay, so what I mean by discrete points is that what we do is uh, we divide entire domain into small elements, which I'll just show you in a moment, and we find the temperatures on those particular points. And what we do is that we use an appropriate energy conservation equation for each of those node points. So those discrete points that we make on the uh, body of interest are called node points. So let's understand this with the help of an example. Okay, so let's say we have a finite difference. Let's say we have a body which looks like this. It has an arbitrary shape. Okay, so this body is divided into a mesh. So it's divided into small square cells or small square elements which have a distance of, or which have dimensions delta x and delta y. And in most cases you will see that the delta x and delta y's are equal, but it's not always true. Like you see on these particular surfaces, your delta x's and delta y's aren't same, and the intersection points right here are called node points. Okay, so these points here are called node points, and what we do is that we define or our objective here is to find the temperature at each of these node points, so that if we have a mesh, or if we divide this particular object into extremely small cells, that means if your delta x and delta y are very small, the temperature at your discrete points will almost appear as if it's a continuous distribution of temperature. Okay, so what we do is that we take a small element. So this element right here, or this control volume or control surface, if it's a 2D, right here is magnified on the magnified view is shown right here for that element, and the temperature of this entire element is estimated by the temperature at the center, by the temperature of at the center point, that is m comma n. So what we assume here is that the temperature of this entire control volume is whatever temperature it is at m comma n. That's the temperature of the node, approximates the temperature of this element. Now uh, in the next slide we'll see how to find the temperature of this element, and for that what we'll do is we'll apply conservation equations on this element, and you will see that the temperature of this particular point m comma n is contributed or is dependent on its neighboring points. That's these points right here. Okay, so let's take this particular element and let's see if we can find uh, the temperature at m comma n. So we start with the heat diffusion equation. So our heat diffusion equation is del square T equals to 0 in 2D, and our assumptions here are that we have constant properties throughout the entire body, and steady state conditions exist. Okay, so this del square T equals to 0 translates to del square T by del x square plus del square T by del y square equals to 0. So we have our temperature uh, varying in x and y direction, and it's in its second order. So now what we do is that we try to write an approximate form of this del square T by del x square and del square T by del y square in terms of uh, delta x's, delta y's, and the temperature of the nodes. That's the temperature of the neighboring nodes and the temperature of the node of interest. Okay, so now uh, let's see what will be the temperature across the half point, that is m plus half comma n, right here, and let's calculate uh, del t by del x at m minus half comma n. That's these two locations right here. So we need to find out how we can approximate uh, or what's the temperature gradient in x direction and between m comma n and m minus 1 comma n, m comma n, and m plus 1 comma n. So our delta t or del t by del x at m minus half comma n will be or can be approximated as, because your delta x's and delta y's are small, your del t by del x can be approximated as the temperature at t of m comma n minus the temperature of at t of m minus 1 comma n divided by delta x, which is the distance between the two nodes. Okay, similarly the temperature at uh, m plus half comma n, that's this location here, can be written as t of m plus 1 comma n minus t of m comma n. So that means this temperature minus temperature here divided by delta x, and let's say this is equation 2. Now what will our del square t by del x square be at these particular locations? So we can write our del square t by del x square as the difference between the gradients at these two locations. So difference between the two, what do I mean by difference between the two gradients? It means the del t by del x, which is the gradient at m plus half comma x, m plus half comma n, minus the gradient at m minus half comma n, that's del t by del x at m minus half comma n divided by delta x. Okay, and this is because we can write our del square t by del x square as del by del x into del t by del x, right? So what I've done is I've just uh, written this del t by del x here in form of del t by del x's, which is here. Okay, and let's see, that is equation 3. Okay, so what we do now is we take equation 1, equation 2. So we take this equation, and we substitute them right here. Okay, we substitute this right here and we substitute this right here, and let's see what we get. Okay, so our del square t by del x square after substitution will be t of m plus 1 comma n. This was nothing but del t by del x at m plus half comma n, minus this was nothing but del t by del x at m minus half comma n divided by delta x. Now if you see, you have a minus sign here and a minus sign here, so t of m comma n will not cancel out, but it will become minus 2 times t of m comma n, and your equation will be del square t by del x square equals to t of m comma n, m plus 1 comma n, that's the temperature at the right node, minus 2 times the node of interest, that's t of m comma n, plus t temperature at m minus 1 comma n, that's the node on the left, divided by the delta x square. So we already had a delta x in the denominator, and after substituting we got another delta x, which made it delta x square in the denominator, and let's say this is equation 4. Okay, so in this similar fashion you can do this exercise in the y direction, where you can take where you can take your derivatives at m comma n plus half and m comma n minus half, and use the node on the top of m comma n and at the bottom of m comma n. And after doing that, the equation that you'll get will be similar to what we found out right now, except it will be in the y direction. So the only change will be that now the neighboring temperatures will not be your temperatures on left and right, but it will be the temperatures on top and bottom. So your del square t by del y square will be t of m comma n plus 1 minus t of m comma n plus t of m comma n minus 1 divided by delta y square, and let's say this is equation 5. Okay, so what we do is that we use a network such that your delta x is equal to delta y. Okay, and substitute delta x equals to delta y in equation 4 and equation 5, or we use equation 4 and equation 5 and substitute it into our heat equation, which is this equation right here. So we've just found out what del square t by del x square is and what del square t by del y square is, and after substituting del y square equal to del x square, we'll get a del x square in denominator right here. Okay, so let's see what equation we get. So the equation that we get is t of m comma n plus 1 plus t of m comma n minus 1 plus t of m plus 1 comma n plus t of m minus 1 comma n minus 4 times t of m comma n equals to 0. So this is nothing but an approximate form of del square t equals to 0. That's the heat diffusion equation. And notice that our node of interest has a negative sign to it. Okay, so whenever you do such problems, make sure that the node of interest, or the node at which you are writing the heat diffusion equation in finite difference form, that's what it's called, has a negative sign to it. It's not necessary that you'll always have a 4. This will your equation will change as your boundary condition changes. Now, because these were internal nodes, uh, you have four neighboring terms contributing to the temperature of T of m comma n. So if you know what these neighboring temperatures are, you can easily find out what the temperature of the node is. Otherwise, you'll have to form a system of equations and solve them, which we'll look with the help of an example later. So what we've seen here is that for node n comma n, the heat diffusion equation reduces to an approximate algebraic equation. So this is no longer a differential equation or a partial differential equation which you need to integrate and find solutions to. This is a simple algebraic equation uh, and which requires you to know the neighboring temperatures. So let's say that you just know two of these temperatures and three temperatures are unknown. So somehow you need to find out or somehow you need to make two more equations so that you get a system of three equations to solve the three unknowns or three variables that you have. Okay, so in this particular case, we had assumed that there is no heat generation involved. But if there is heat generation involved, we'll have a Q triple prime term in the original heat diffusion equation. And for that equation, we had assumed that K was constant. And because we had a zero on the right hand side, we just uh, we just assumed that our equation was del square T equals to 0 because uh, we had a 0 on the right hand side, so the K did not matter. But now because we have a heat generation term, we'll have to consider the thermal conductivity as well. So with heat generation, our equation uh, can be approximated as K times the, so this is K times del square T, okay, plus Q triple prime equals to 0, and our del square T can be written as the summation of the neighboring temperatures. So T4 means that it's the summation of the four neighboring temperatures minus 4 times T, that's the node of interest, divided by delta x square times a K plus Q triple prime equals to 0. So this makes our equation as T of m comma n plus 1 plus T of n comma n minus 1 plus T of m plus 1 comma n plus T of T at m minus 1 comma n minus 4 times T at m comma n plus Q triple prime into x square by K. So what I did here was I divided this equation by K. So I divided this equation by K and multiplied it by delta x square. So on multiplying it by delta x square, this delta x square gets cancelled out, and by dividing it by k, this k here gets cancelled out, whereas you'll get a k term in the denominator of the heat generation term and a delta x square in the numerator of the heat generation term. Okay, so this equation here is similar to the equation on the top, except that we have an additional heat generation term to it. Okay, so let's look at another approach of finding the node point and where the boundary conditions are a bit complicated. So the the scenario that we looked at before had all neighboring cells, and all of them were interior nodes. So they weren't, so those were nodes which were inside the boundary and did not share any, uh, did not, weren't on the edge or on the surface of the boundary of the body. So let's see how to solve a problem where you have, say, one of the surfaces exposed to uh, air at T infinity and with a heat transfer coefficient of H, and you have heat being transferred to that particular element through convection. So your control volume will look something like this, where you have heat being conducted from the four neighboring cells plus heat being convected from the surrounding air, which is at T infinity, to the node T of T at m comma n. So you have an additional mode of heat transfer here, whereas in the initial scenario we just had conduction. So let's see how we'll solve this problem. So we always begin in this particular scenario, it's best to start with energy balance equation. So in the previous problem, remember that we started with the heat diffusion equation. This is a different approach, so I'll just show you how we can get the temperature distribution by starting from the energy balance equation. You can use this approach in the previous scenario as well. So our energy balance equation is E dot St equals Qn minus Q out plus Qgen, and our assumptions are that the system is at steady state and there's no heat generation in the system. And if you look at the arrows of the control volume, what we've assumed is that Q is coming into this control volume or control surface from all directions, and we haven't assumed any Q going out. Okay, so if that's our assumption, because it's steady state, this term will go to zero, because we have assumed that there's no heat Q going out. Your Q out will be 0, and because there's no heat generation, the last term will be 0 as well. So our energy balance equation reduces to Qn equals to 0. Now, how will you write Qn? So you have five heat transfer rates by which heat is being transferred into this particular control volume or element. So one is conduction from n minus 1, one is conduction from n plus 1, one is conduction from m plus 1, and one is conduction from n minus 1. So you have four conduction terms and you have one convective term. So our Qn can be written as Q coming from n plus 1 to m comma n, n minus 1 to n comma n, and m plus 1 to n comma n, plus m minus 1 to m comma n, and Q infinity to m comma n, which is nothing but Q convection. Okay, so how will your how will your Q m comma n plus 1 to n m comma n look like? So how will the conduction look like? So we just apply Fourier's law, the approximate form of Fourier's law. So what we've done is that, so our Fourier's law is nothing but minus k times dt by dx, and because we are not looking at heat fluxes, we are looking at a heat rate, we'll have to include the area as well. So our Fourier's law will be minus k a, that's the area across which heat is being transferred, multiplied by dt by dx. Now because your element size or dx is so small, you can approximate your minus ka times dt by dx as minus k times A into delta T by delta X. Okay, so your equation will be minus K times whatever area is through which heat is being transferred, multiplied by uh, T2 minus T1 divided by delta X. Okay, so if it's in X direction, it will be delta X. If it's in Y direction, it will be delta Y. So let's look at our first term, that's Q, that is being transferred in the Y direction. So our Fourier's law will be K times area, and I'll tell you where the negative sign went in just a bit. So we have a K times area. Now it's very important to consider the appropriate area. So in this particular case, if you see, the area of interest is this particular area right here, which has a length of delta X, and let's assume that the uh, element size is a unity into the page or outside the page. So in the Z direction, so your area will actually be delta X times delta Z, right? So this will be your area. So what we've assumed that your delta Z is 1. Why? Because we're assuming a 2D conduction. Okay, so your delta Z is 1. This is your area times delta T. So this right here is should have been T2 minus T1, which is T of m comma n minus T of m comma n plus 1. But because we had a negative sign in the original Fourier's law, I have flipped uh, these temperatures. So now you have temperature coming from m comma n plus 1. Yeah, so you have your Fourier's law as T of m comma n plus 1 minus T of m comma n divided by delta y. So we've assumed that your Q conduction here is positive, so that means your T of m comma n will be at a lower temperature as heat is flowing from higher temperature to lower temperature, and your right hand side will be positive as well. So that's why I don't have a negative sign here. I've just skipped a step and have flipped the temperatures uh, inside the bracket. So let's look at your heat in the X direction. So what is the heat? How will you write the conduction coming from left to right? So your thermal conductivity will be K, and your area in this case will be delta Y times delta Z. So it will be this area right here. Okay, and because we have 2D, we have assumed we are just looking at a 2D conduction, our delta Z will be equal to 1. So your area is delta Y times 1 into again T of the two temperatures, T of m minus 1 comma n minus T at m comma n divided by delta X. So notice one more thing, because heat was being transferred in the y direction, we had a delta y here, and because it's being transferred in the x direction, we have a delta x in denominator right here. Okay, so in a similar fashion, we can write down temperatures. Let me just erase this. So we can write down temperatures in I'm so sorry about this. Okay, we can write down the temperatures in the other direction, Q conduction coming from the other two directions as well. Now this is important because now our element size in this direction, let me just draw it in a different color. So the heat that is being transferred from right node to m comma n is just being transferred through a delta y by 2 area, right? So your area when you consider conduction will just be, so your area in this case will be delta y by 2, because that's the area across which conduction is taking place, times delta z. Okay, but your delta z is 1, right? However, and the temperature difference T at m plus 1 comma n minus T at m comma n divided by delta x. So the temperature is still being transferred across a distance delta x. So this distance right here is still delta x. So we have a delta x in denominator, but for the area we have delta y by 2. Now similarly, for heat being transferred from n minus 1 to m comma n, that's from bottom to m comma n, our Fourier's law can be approximated as k times a. Now area in this case is again the area of interest is just this much, and it's not the entire delta x distance. So we have a delta x by 2 multiplied by delta z, which is 1, times the temperature difference T at m comma n minus 1 minus T at m comma n divided by delta y, because that is the distance across which heat is being transferred. So whenever you apply energy balances and your elements or your control volume isn't um, a perfect square or a perfect rectangle, you need to make sure that the areas and the lengths that you consider are appropriate. Okay, so that's why I've taken this example, so that if you get such problems in future, you know what area to consider and what length to consider. So now we have the four terms, the four conduction terms. We still need to find out what our convection term is. So let's look at that. So our convection term q infinity to m comma n will be h. So this is nothing but we'll use our Newton's law of cooling, which is, let me use the red pen. So our Newton's law of cooling is Q convection is HA times T2 minus T1. Okay, so T2 minus T1, and T2 is always the whichever temperature is greater. Okay, so in this case, because heat is flowing from the surrounding through the node T m comma n, we know that T infinity has to be greater than T m comma n. Okay, so now you have convection, or you have heat being transferred through convection through two surfaces. That's, you have a convection heat rate in y direction, and you have a convective heat rate in an x direction as well, in a negative x direction as well. So you have two different areas of interest here. Okay, so what we do is we divide the convection into two parts. First we write how much heat is being convected in x direction or in y direction, and how much heat is being convected in the x direction. So h is our convective heat transfer coefficient times our area. Again, the area of interest is just this much, so it's not the entire delta x, but it's just delta x by 2. So delta x by 2 times delta z, so this is delta z, which is equal to 1, times the temperature difference T infinity minus T at m comma n plus convection in x direction, that's h, times delta y by 2, that's the area which is right here, times delta z, which is equal to 1, multiplied by the temperature difference T infinity minus T m comma n. Okay, now what if our delta x was equal to delta y? So assume that we draw a mesh or a nodal network where your delta x is equal to delta y. Our equations will reduce down to T of m minus 1 comma n plus T of m comma n plus 1 plus half, and that's because our areas were half, that's why we have the half factor here, half of m plus 1 comma n, which was the node at right, plus m comma n minus 1, which is the node on the bottom, plus h into delta x by k into t infinity. And I want you to do the math, so take all the q's that we found out and substitute it into the equation that we had in the previous slide and see if you get this particular equation. So we have a convective term which is h times delta x by k into t infinity minus 3 plus h into delta x by k times t of m comma n. So even here our node of interest is associated with a negative sign, but the coefficient for t of m comma n is not 4, but it's a different number, or it's a different value which has contribution through convection as well. And now the temperatures that are contributing to the temperature of n comma n are the four neighboring temperatures. So they are the four neighboring temperatures plus the temperature of the surrounding air. So we have five temperatures that are contributing to the temperature of m comma n. So this is how you use energy balance equation to find out the temperature distribution or temperature of any particular node. So this is the equation that you get when you apply, let me just, when you apply energy balance at m comma n. Okay, so table 4.2 in your textbook has a summary of different types of nodal finite difference equations. So it lists a bunch of different equations where you have different boundary conditions and the location of the node is different. So in this particular problem, we had assumed that the node is an interior node. It's partially interior, but one of its boundary or one of its surface is exposed to air. You may have this node on the boundary itself, and your entire node can be exposed to convection. So this can be your boundary which is exposed to convection. You may have the node exposed to a constant heat flux or insulated. So there are different types of boundary conditions, and table 4.2 gives you the equations for uh, these different scenarios. So please go to table 4.2, understand what the boundary conditions are and what the location of the nodes are. So your node can be an interior node, it can be on the surface, or it can be a corner node, and your equations will be different in all these scenarios. And in future, whenever you are solving a problem, you first need to see if you can apply any one of these equations in equations given in table 4.2. You may have to tweak it a bit, so your equations in table 4.2 may be given for x direction, but you may have similar conditions but only in y direction, so you may have to like flip the temperatures and replace your delta x by delta y's. So you need to be smart about that, and you need not like start from your energy balance equation and waste time. You can just use those equations.